Good morning, everyone. My name is Jinglun Li from Fudan University and JIIOV Technology. Today, I'll present our work accepted at ICCV 2025, SynOOD synthesizing near-boundary OOD samples for out-of-distribution detection. In real-world applications, deep models inevitably face out-of-distribution samples. Although clip-based vision language models are powerful, they often fail on challenging near-boundary OOD cases. These samples look very similar to in-distribution images and are easily misclassified. Our goal is to improve boundary-level discrimination in OOD detection. Our key idea is simple but effective. We generate synthetic near-boundary OOD samples using foundation models and fine-tune CLIP with them. By doing so, CLIP learns from much harder examples and becomes more robust at distinguishing IND and OOD samples. The SynOOD framework has three parts. First, we use an MLLM plus a diffusion model to generate boundary OOD images. Second, we fine-tune the CLIP image encoder with a projection layer. Third, we refine negative label text features in the CLIP text encoder. Together, these steps significantly improve the detection of difficult boundary cases. For OOD image generation, we first use an MLLM to extract contextual elements from an in-distribution image, such as bamboo or railing in a panda photo. Then we iteratively guide a diffusion model to replace the main object with these contextual elements. We further use gradients from OOD scores to refine the noise, pushing the samples towards the IND/OOD boundary. As a result, the images remain natural and realistic, but are semantically shifted away from IND. Next, we fine-tune CLIP. For the image encoder, we freeze the backbone and only train a projection layer, aligning synthetic OOD images with negative labels. For the text encoder, we make a subset of negative label features learnable, so they adapt to the synthetic OOD samples. This dual fine-tuning leads to a much clearer separation between IND and OOD. We evaluate on ImageNet 1 as in-distribution and test on iNaturalist SUN, places 365, texture, and the OpenOOD benchmark. Synthetic images are generated using Stable Diffusion 2, guided by LLaVA prompts. The computational overhead is very small, less than 1% additional parameters, and about 2 milliseconds per image. Results show SynOOD achieves state-of-the-art performance. On ImageNet benchmarks, we improve AUROC by 0.36% and reduce FPR95 by 3.24%. On OpenOOD, our method performs strongly on both near OOD and far OOD scenarios, even with only 50,000 synthetic samples, outperforming methods that use millions of real images. We also conduct ablation studies. They show that iterative generation is more effective than direct text-to-image generation. Fine-tuning both the projection layer and negative label features gives the best results, and the improvements generalize across different CLIP backbones, including ResNet and VIT. Here are some visualizations. On the top row, we show original ImageNet images, and on the bottom are synthetic OOD samples. They are visually realistic, but semantically different. For example, lipstick becomes flowers, or a cheeseburger is decomposed into its components. These are exactly the challenging near-boundary cases we want the model to handle. To conclude, we propose SynOOD, the first framework to synthesize near-boundary OOD samples with MLLMs and diffusion models. With minimal extra costs, SynOOD significantly boosts OOD detection performance. We believe this opens a promising direction for using generative models to enhance robustness in OOD detection and beyond. Thank you.